All right, this is solving exponential and logarithmic equations. Chapter 7, section 6. First off, exponential equations are an equation in which the variable expression occurs as an exponent. So basically, you have a variable in the exponent. An exponential equation, the parent function is y equals a b to the x. And I think in previous sections we've talked about the child function looking like this. Okay. Basically, you have a variable. Now, it might be a lot of, like one variable and some numbers or subtraction or multiplication. As long as the variable's in the exponent, it's an exponential equation. Logarithmic equations, an equation that involves logarithms of variable expressions. So basically what you're looking at is you're looking at the fact that you have, let's see how we can write it. It involves a log with some variable in here. So that's a logarithmic equation. This is the child function of a logarithmic equation. Log base b of x minus h plus k. As long as there's taking the logarithm of a variable, it's a logarithmic equation. A logarithmic equation is not something that has this. Right? This is not a logarithmic equation. The variable is not part of the logarithm. It's being added to it. So this is not a logarithmic equation. Properties of equality for exponential equations. This is a kind of a logic property. Basically, if you look at this, if b is a positive number other than 1, then b to the x equals b to the y, if and only if x equals y. Basically, what this is saying is if you have 2x equals 2y, don't these variables have to be the same? This side equals this side. They have to be the same. That's why if you say 2 to the power of x equals 2 to the power of y, the variables have to be the same. If you have 2 squared equals 2 to the y, then logically, since x equals y, then here y has to equal 2. It can get a little more complicated only because, you know, it could be y, or 2 to the 4th power equals 2y plus 1. 2 to the 2y plus 1. But you still look at the exponents. This exponent should equal this exponent. So to answer this next part, if 5 to the x is equal to 5 to the 4th, then x equals 4. And if x equals 4, then 5 to the x should equal 5 to the 4th. So let's take a look at the first example from the note-taking guides. Actually, I'll do a couple quick ones here. If you have 2x equals 2 to the 3rd, then the answer is x equals 3. Now, this is the real reason. This is the logic. You just assume that they're equal. But how do you undo, from previous sections, how do you undo an exponential of base 2? Well, you take the log of base 2. You take the log of base 2. They cancel out, and x equals 3. Now, you don't actually have to do that. You can just simply say that the exponents have to be the same. Now, in the first example, if the bases are not the same, like if this is 4 to the 3rd, well, 4 and 2 are not the same. So you have to first say, I wish 4 was a 2. And you have to use exponents. So this ends up being 2 to the x plus 1. And 4 is 2 squared. So basically, now that the bases are the same, this exponent has to equal this exponent. So x plus 1 equals 6. X equals 5. Once you get these answers, plug them into the original equation, and you'll see if you get it right. So take a look at this. This first example is a big leap from even this one here. 64 to the x power equals 16x plus 1. This is the original equation. These are not the same bases. We have to somehow write them the same way. So I need to think about what is 16. 16 is 4 squared, so you could use that. Rewrite each base with a base of 4. That means this is 4 squared, and this is 4 cubed. If you didn't know that it was 4, it could also have been 2, and you'll still get the same answer. So let's do some work here. First of all, you have to remember power of a power property. That means we're taking power of a power. That ends up being 4 to the 3x power. And now here we have 4 to the 2. So the 2 gets distributed onto the x and onto the 1. So 2x plus 2. Now we're using the power of equality. That's just a logic statement. If 4 to the 3x is equal to 4 to the 2x plus 2, then those exponents must be the same. And now it's a matter of solving for y. You solve for y here by minusing 2x. 3x minus 2x gives me 1x. And all you're left over with is a 2. So the solution is x equals 2. Now, if you type that into your calculator, it says here to check. Substitute 2 in for x. 64 to the second power equals 16 to the second power plus 1. So that should be 64 to the squared, which if you type in your calculator is 4096. And then 16 to the 2 plus 1. That is 16 cubed, which is also 4096. So we have now checked the solutions and we know we are correct. So let's take a look at this. Sometimes you can't make the bases the same. Sometimes you can't go over here and make the 6 and the 27 the same. Yes, they're both divisible by 3, but you cannot make them the same. So it says here to write the original equation, and then you need to take the log with a base of 6, because as I said earlier in the video, I think it was right here, what undoes an exponential of base 2? Well, a log base 2. They are inverse operations. So what undoes a exponential base 6? A log base 6. So now we've got log base 6 of 6 to the x, and then log base 6 of 27. So this here cancels and gives us x, and then we have log base 6 of 27. Now over here it tells us to rewrite it in some way, but I wouldn't worry about this. Just use the change of base formula. In the change of base formula, you will do log of the big number divided by log of the little number. And please make sure you put parentheses around the numbers. Once you do that, you should get an approximation of 1.84. So the solution here should be 1.84. Logarithms will help you solve exponentials. So we first here's example 3. We need to solve for x. we cannot get rid of the base e until the 6 and the plus 8 are gone. That's why here it says subtract 8 from both sides. So we end up with a 12. We still can't get rid of the base because there is this 6 in front. It's multiplication, so we get rid of multiplication by dividing, and we divide by 6. The 6's cancel on this side, which leaves us with e to the 0.25x. It is equal to 2. So what we have here is e to the 0.25x equals 2. There's no way to make the base e and base 2 be the same number. So what we have to do is we have to undo a natural base. Again, exponential with base e, you undo that by taking a logarithm of base b. So it says take the natural logarithm of each side. So we're taking ln e to the 0.25x equals ln 2. This, the natural base and the natural log cancel. 0.25x is all that's left. And ln 2. Here, multiplication is going on between those two variables. So we divide each side by 0.25. When we divide each side by 0.25, we end up with something approximately 2.77. You should check this by plugging it back into the original equation. We're going to move on here, though. Take a look at checkpoint number 1. This is also from your note-taking guide. We have a base of 3 and a base of 9. We could try to get rid of them using logarithms, but first, take a look at 9. 9 can be rewritten as 3 squared. That's when you all should know. 9 is 3 squared. Because now all we have is we have the equal exponents. This exponent has to equal this exponent for this to be true. So 7x plus, 7x minus 3 should equal 4x. Now some of you might be saying, where did the 4x come from? Right here, 2 times 2x gives me 4x. Now from here you can do whatever you want, really. We need to get the variable to one side, so let's subtract 4x from both sides. 3x minus 3 equals 0. Let's add 3 to both sides. 3x equals 3. Now let's get rid of that multiplication and get that x equals 1. So if you put a 1 in here, you should be able to check to see if you get the right answer. Checkpoint number 2, 5 to the x power equals 72. There is no way to make a 5 and a 72 have the same base. This is where we need to use logarithms. An exponential base 5, I've said this many, many times, exponential base 5 is undone by a logarithm base 5. So like I said, exponential base 5 undoes a log base 5, so you do that to both sides. And what we have, this cancels. The exponential base 5, the log base 5 cancels out. So you have x equals log 5 base 5 of 72. And this is where the change of base formula comes into play. In your calculator, you do log of 72, divide it by log of 5. That'll give you an approximate answer of, there's an x here. That'll give you an approximate answer of x equals 2.657. Now, when you plug this number, this is an estimation. So when you plug this number back into the original, it'll get you very, very close to 72. Not exactly, but very, very close. Some more examples here. Let's go through this. more checkpoints. This is from your note-taking guides. We can't do anything about getting rid of the exponential until this minus 6 is gone. And there's no way for us to make a base of 11 look like a base of 8. So since there's no way to do that, you have to take a logarithm. Now, we're taking the log. Here's an exponential of base 8. So we need to take a log of base 8. Because, again, for the fourth time, an exponential base is undone by a log base. So that cancels. You get 3x plus 2 equals log base 8 of 11. Now it's a matter of calculating the rest of this out. Let's subtract 2 from both sides. And I'm going to leave it out front just so there's no confusion. And then divide by 3. So x equals, this is the exact answer. And really what you're going to want to do is to use the change of base formula to do this, to estimate your answer, and then use that decimal to solve the rest of this. It'll be very difficult for you to plug this into your calculator. But you should then end up with that the answer should be negative 0.2823. Number 4 checkpoint. Same thing as over here. You cannot get rid of the base until the minus 6 is gone. So here we got to get rid of the plus 2. And you should notice that this exponent is not attached to the e, or to the 3. The exponent's not attached to the 3. So we undo this 3 by division. So we now have e to the 0.5x equals 1. Now we could go, there's a lot of ways you could go about doing this, but let's undo a natural base. You undo a natural base by ln, by lnning both sides. So 0.5x now, this cancels. 0.5x is then equal to 0, which means our answer x is equal to 0. Right? This undoing of the bases is what will probably be the easiest method for you to use. All right, guided practice now. Guided practice. So our first guided practice, we're going to do number 1. We've done a lot of examples so far. So 9 to the 2x equals 27 to the x minus 1. This is number 1 from the guided practice in the textbook. 9 and 27, they are not the same. There is no way to make 27 into a 9 using exponents. But 9, hopefully you're all saying, is 3 squared. 27 is 3 cubed. And now what we have is we have the same base. Therefore, these exponents have got to be the same. 2 times 2x equals 3 times x minus 1. So that becomes 4x. This is 3x minus 3 because you distribute the 3 into the parentheses. We subtract 3x from both sides, and you get that x equals negative 3. This is how this is set up. Let's look at number 3 quickly. See if we can't knock this one out. 81 to the 3 minus x power is equal to 1/3 to the 5 x minus 6. Now, this has a fraction in it, right? You all see the fraction there. That may make things difficult unless you remember the negative exponent property of exponentials. 1/3 is actually 3 to the negative 1. 1/3 is 3 to the negative 1 power. You basically take this that has a positive exponent and you make it negative by putting it in the numerator. 3, base of 3, you can make 81 3 to the 4th to the 3 minus x. And then here is equal to 3 to the negative 1, 5x minus 6. So, same base, exponents are the same. 4 times 3 minus x equals negative 1, 5x minus 6. Okay, I kind of ran out of room there, so let me erase some of this other stuff here. All right, so what we have here is we've got, let me rewrite this now. 4 times 3 minus x equals negative 1 times 5x minus 6. I'm going to let you solve this the rest of the way, but you should end up with an x equals negative 6. If you don't get this, you should come in to ask what mistakes you made and how you didn't come up with the right answer. All right, that should help you with a number of the problems from the homework. Now we get to the properties of equality for logarithmic equations. It's exactly like the exponentials. If you have log of the same base, then this part should equal this part. So only if and only if x equals y. Here, log base 3 of x should equals log base 3 of 8. That means x equals 8. And this is y. How do you undo a log base 3? Remember, exponentials, logarithms, they undo each other. So this means this is 3 to the power, 3 to the power. Cancels out, x equals 8. So take a look over here. Solve this. You can just logically know log base 7, The property of equality says that the 6x minus 16 is equal to x minus 1. If you don't like that logical property of equality, just remember what undoes an exponential. What undoes an exponential? So, what undoes the exponential? And the logarithm. What undoes a logarithm? An exponential of the same base. That cancels, leaves us with 6x minus 16. This cancels out, leaves us with x minus 1. So either way works. For us, let's go ahead and subtract something from both sides. So let's subtract x from both sides. So we're going to minus x from here, we're going to minus x from here, and we're going to get 5x minus 16 equals negative 1. Then we're going to add 16 to both sides because we need to get rid of those constant numbers. So 5x equals 15. Here it's 5 times x, so we divide to get rid of multiplication. Divide by 5. And x equals 3. So our solution is 3. You check by plugging in that information. You check by plugging it in and doing 6 times 3 minus 16 should give you 3 minus 1. So this is 18 minus 16, which is 2. This is 3 minus 1, which is 2. And our solution works. We're going to go through some more examples here. This one right here. This one, you do not have the same logarithm. Please remember that. The only way we've been able to use the property of equality is when they had the same base, or when they had the same logarithm. This one, you just have to, this word is a fun looking word, exponentiate each side using base 5. So 5 to the power, 5 to the power, cancels out. All that's left is 3x minus 8 equals 5 squared. 5 squared, everyone, you should know 5 times 5 is 25. And basically, instantly, this nice looking equation, or this ugly looking equation, has become an equation that you've been solving since middle school. Add 8 to both sides, divide each side by 3, and you get 11. You should always check your answers. If you want to make sure you get the right, you're right, you should check your answers. So plug 11 in. You get log base 5 of 25. You could use the change of base formula. You could do whatever you want. But basically what you get is that you get 2 equals 2. You get a solution that actually works. Alrighty, look at this. We have to remember some properties of logarithms. You can't just undo both these logs. You can't move it to the other side because then you still wouldn't have the logarithms by itself. But we do know when you add logarithms, it is the product property. That means you take the first log, the 5x, and you multiply it by the second log, which is x minus 1. So you get, basically, you get log, let's see, let's distribute here. So it's 5x times x, log 5x squared. You're multiplying 5x times minus 1 minus 5x equals 2. At this point, you cannot get rid of, you can't use the equality property. You have to exponentiate. This is a common logarithm. Common logs are base 10. So to undo a common log, you exponentiate it by a base 10. So all that's left is 5x squared minus 5x equals 100. So it's to do the distributive property. Basically, I've already done that. So we're going to jump to in standard form, 5x squared minus 5x minus 100. We're going to minus 100 from both sides equals 0. Here it says to divide each side by 5. You don't have to divide by 5, but that is a common factor amongst all of those. And you end up with an equation that looks much, much nicer. And you can factor, you can graph, you can synthetically divide, you can use the graphing calculator. You can solve this many, many ways. I'm going to factor it because I know factors of 20 are negative 5 times positive 4. When I add them together, it works. And you should get answers of 5 or negative 4. If you had trouble with this part right here, that's from chapter 5 and 6. You're going to want to come in and get some help. So let's see here. I don't want this video to be too long, so let's do the checkpoints so that your notes are taken care of, and then we'll skip the guided practice so you can just get started on your work. Alright, solve the equations, check for extraneous solutions. Extraneous solutions are solutions that do not work. So, number 5 from your guided practice. They should be showing all of these steps when you watch these videos. Natural logarithm on both sides. Since they're on both sides, all you have to do is undo a logarithm. Natural log is undone by a natural base. Or use the logical property of equality that says all that really matters is that this part ends up having to equal this part. So 7x minus 13 has to equal 2x plus 17. And when you solve this, minus 2x, the 8th grade math classes are working on solving equations with variables on both sides. Add 13, 5x equals 30, divide by 5, x is 6. Over here, notice you only have one logarithm. You do not have a logarithm on both sides, so you cannot use the equality property. You actually have to undo a log base 3. That log is undone by a exponential base 3. And once you do that, you still end up with an equation that you've been solving since middle school. 2x plus 9 equals 27, minus 9, 2x equals 18, divide by 2, x equals 9. And then you check to see if they work. The next part, over here, still, notice, logarithm, they are not the same logarithm. So you have to undo a log base 4 with an exponential base 4. 10x plus 624, because these cancel, is equal to 4 to the 5th power. Now, 4 to the 5th power is 1024. So you now have 10x plus 624 equals 1024. So, from here, again, solve for x. 10x equals 600. You divide by 10. Oh, I jumped ahead here. Hopefully you noticed that I made a arithmetic mistake. 1024 minus 624 is 400. So when you divide by 10, you end up with 40 as your x value. And what would have happened is you would have checked this answer to see if it was correct. And when you checked, you would have seen a problem, and you would have come back, found this error, 400 divided by 10, and you would then see that the correct answer is 40. All right, take a look now at the last example. This is where, again, we have to condense. Log base 6, log plus log base 6, that is the product property. So it should be log base 6 of x minus 9 times x equals 2. And now you can actually get rid of the logarithm. X minus 9 times x equals 36. This right here is 36. Distribute. Minus 36 from both sides. And now you've got a quadratic that you should be able to factor, graph, synthetically divide, quadratic formula. There are a lot of ways to solve this from this point. You should end up with, let's see here, x. Set up some factoring. Factors of negative 36 that add up to negative 9. After going through all of the factors of 36, you should notice that minus 12 times a positive 3 gives you a negative 36. And a minus 12 plus 3 gives us the minus 9. So my zeros, my solutions are 12, negative 3. Now, When you plug those back in, some of those numbers will give you a wrong answer. Some of them will say error. They won't work. You'll get 5 equals 2 instead of 2 equals 2. When you do that, you should get that 12 is your final answer. So we're going to go ahead and skip guided practice 8 and 10. We're going to let you just go ahead and work on practice problems 7.6, 1 through 53 odd, and so on. So good luck with that. If you have any questions, you really should be working on the rest of the guided practices. You should be working on some of the practice problems so you are aware of what questions you have when you come in. Thanks for watching.